We want to describe topological properties of differentiable manifolds, but even if we were just interested in manifolds without boundary, we need to consider manifolds with boundary and their submanifolds. Anyway, we do not want to introduce artificial complexity in the theory, so we prefer to work with submanifolds of manifolds with boundary that are transverse to the boundary of the ambient space, the so-called net submanifolds. And indeed, that's not going to reduce the generality of our study. As an example of this, we are going to see that under the right hypothesis, if we have a differentiable map defined in a manifold with boundary, and we consider a regular value, we are going to define what a regular value is in this context, then the preimage of the regular value is an its submanifold. So we are going to define submanifolds that are well placed with respect to the boundary of the ambient space. That's the idea. Consider M a delta manifold, a manifold with non-empty boundary. And we say that N is a neat submanifold if the boundary of N is equal to N intersection the boundary of the ambient space M, that's the first condition, and besides that, N is covered by the domains of local charts of M such that N intersection U is the preimage of this linear subspace Rn times 0. So that's what that's the two parts of the definition. There is nothing else. Why are neat submanifolds interesting? The reason is that a neat submanifold is a submanifold with or without boundary, such that, first of all, by the definition, the boundary of the neat submanifold is the intersection of A with the boundary of M. But it's not just that what we get. A is going to be transversal to the boundary of M. Okay, so let's try to understand that a little bit better, right? We have that the boundary of the neat submanifold is the intersection of N and the boundary of M. And now we can consider a point X that belongs to the boundary of M. By the definition of neat submanifold, there exists a local chart such that well, obviously the local chart contains the point X, and that satisfies too that the intersection of N and U is the preimage of Rn times 0. Okay, we have that. We also have a second property, and that is not related to the neat submanifold. It's just a description of the boundary of the ambient space at a neighborhood of one of the points of the boundary. And indeed, what we have is that the intersection, sorry, it's the other way around, the intersection of the boundary of M and U is just the preimage of lambda equals 0, where lambda is a linear map from Rm to R. The two linear subspaces Rn times 0 and lambda equals 0 are indeed transversal. Because since this subspace over here, okay, is of codimension 1, the unique way in which these two subspaces are not transversal is if Rn times 0 is contained in lambda equals 0. But that's not that's not possible, okay? If we have Rn times 0, and we suppose that that's contained in lambda equals 0, then by the definition of n intersection u, sorry, what we get is that n intersection u is contained in the boundary of m intersection u, right? And in that case, n intersection u is going to be contained in n intersection boundary of m intersection u, but that's the moment of using that n intersection boundary of m is the boundary of n. So we get that this is contained in the boundary of n intersection u, so that every point of our manifold n in the open set u is indeed a boundary point. That's not possible. That doesn't happen for our manifolds with boundary. So this situation is absolutely impossible, and in particular, that implies that these two linear subspaces are n times 0 and lambda equals 0 are transversal, right? But this implies, in particular, that in the open set U, n, in U, by using that the local chart is a diffeomorphism, in U, we have that, that n and the boundary of m are indeed transversal. So we get what we wanted. Indeed, the boundary, because of course we know that n intersection boundary of m is the boundary of n. We get that n and the boundary of m are transversal. And indeed, as a consequence of that, the boundary of n is the intersection of these two submanifolds that are transverse, and because of that, the dimension of the boundary of n is the dimension of n minus 1. Because what you have in here is that this has some codimension, and it is going to be whatever, let's say q. Here we have that the boundary of n has codimension 1, so the codimension increases, the sum of the codimensions increases by 1, so the dimension of the boundary is the dimension of n minus 1. So we are in this situation in which, of course, that's something that we already knew, that the boundary of a manifold with boundary has dimension that is one less than the dimension of the manifold. But we are just checking it out again. And what we get is that a neat submanifold is indeed a submanifold with boundary such that the boundary of our neat submanifold, sorry. What is a neat submanifold? It's a manifold with boundary that is transversal to the boundary of the ambient space. Okay, that's the definition. So let's consider some examples. In these examples, n is going to be these curves, the candidate to be an its submanifold, and M is just a closed disk in the three cases. Okay, so let's go with the third one. In the third one, we can calculate the intersection of the boundary of M with M, and also, we can calculate the boundary of N and then the intersection of the boundary of M and N. For an its submanifold, these two sets are equal, but that's not the case for our third example, because the set on the right-hand side is indeed empty. There are no points of our segment in the circle, whereas the boundary of N contains 2 points. So this is a manifold with boundary. The manifold N over here is a submanifold with boundary of M, but it's not an its submanifold. Okay, let's go with second example. In the second example, we have a problem, okay, with this point over here. Because again, in a neighborhood of a point that it is that belongs to N, what happens is that N is going to be locally a manifold with boundary, but a manifold that is transversal to M. So the picture is going to be like this, okay? And here we're not in that situation. We're not going to be in a situation in which we have transversality. So this submanifold over here is not neat. You can actually consider that as a submanifold, even a submanifold without boundary if you want, because you could consider this just as the image of the circle. But it is not going to be ever an its submanifold. So this is a non-neat case, right? And the first example is a neat submanifold. In this case, yeah, we are having here an arc. The arc is a manifold with boundary. The two boundary points are on the boundary of the ambient manifold, so good, the first condition holds. And besides that, we have that in the neighborhood of these 2 points, our neat submanifold is transversal to the boundary, is transverse to the boundary. So yes, this is a situation where this set over here is a neat submanifold of the closed disk, right? So it's a situation in which we want to have submanifolds whose boundary is contained in the boundary of the ambient space, but we want transversality in the boundary of the ambient space between our neat submanifold and the boundary of the ambient space, okay? We have a regular value theory for delta manifolds. Let's see this. Consider M and M CR delta manifolds. Okay, here we could have that, for instance, the manifolds could have empty boundary. That couldn't be a problem. And consider a CR map F from M to N. Assume that Y is a point that belongs to N, but it is an interior point. And assume that it is a regular value for both maps F and the restriction of F to the boundary of M. Those are two differentiable maps. So the preimage of Y is a CR knit submanifold of M. Okay? We want to see that. There are two situations here. The first one is that we consider a point in the preimage of Y, which is indeed an interior point, right? In this case, since X is by hypothesis a regular point, what we have is that the preimage of Y is a submanifold in the neighborhood of X. The simplest case of submanifold is a submanifold without boundary locally. Okay, no problem with that. Indeed, we can actually say what the codimension of this submanifold is. It's just the dimension of n. So this case has no problem. Indeed, we are just applying the regular value theorem for the case in which there are no boundaries, because yeah, y is not in the boundary of n and x is not in the boundary of m. So we're just applying what we already know. The situation that is more interesting, though, is what happens is if X is a point in the preimage of Y, which is indeed a boundary point, right? So let's see if I can make this clear. The first thing that we have to realize is that X is a regular point for F. So locally, the preimage of Y is a submanifold of codimension equal to the dimension of n, right? And we know that indeed the tangent space of the preimage of Y at the point X is just the kernel of the differential of F at the point X, which is a map from the tangent space to M of M at the point X to the tangent space of N to the at the point Y. Okay? Right. But we know too that X is a regular point not just for F, but also for the restriction of F to the boundary of M, right? And so that implies that in the boundary of M, the preimage of Y is also submanifold, whose codimension is again the dimension of N, right? But let's consider something that it is very interesting too, is that the tangent space of the preimage of Y intersection the boundary of M is the kernel, because we are considering regular points and regular values, of the differential of f at x, but now the domain of the differential is going to be considered as the tangent space of the boundary of M at the point x, right? And what we can see is that what we know is that the codimension of this space, because we are working with regular values, is indeed the dimension of n. And here, the codimension of this second kernel is also going to be the dimension of n. So the codimension of these two spaces are the same, right? But the dimensions are different, right? Because the first kernel, the first linear map is defined in the tangent space of M at X, and the second in the tangent space of the boundary of M at X. So if these two kernels have the same codimension, that means that the dimension of the second one is the dimension of the first one minus 1, right? So we have the dimension of the tangent space. Okay, so in particular, let's see what we can say. What we have, okay, is that the kernel of the differential of f of x, where the domain is considered in the tangent space of the boundary of M at the point X, is contained and different than the kernels of the differential of f at x, but now considered at the tangent space of M at x, right? Okay, let's call the first one, for instance, n sub 1. And what we know is that n sub 1 is just the tangent space to the preimage of y at the point x. And what we are actually saying is that that's not contained in the tangent space of M at the point x. Because if n1 is contained in this tangent space, these two kernels are the same. So in particular, that implies that the linear subspaces n1 and the tangent space of M at x are transversal, right? Yeah, consider as subspaces of the tangent space of M at the point x. The second one has codimension 1, and so the unique way in which they couldn't, the unique possibility for them not being transversal is if n1 is contained in the tangent space of M at x, and we just saw that that's not happening, right? So in particular, that implies that, okay, the preimage of y is transversal to the boundary of M at x, but that happens for every x, okay? For every x, which is actually in the preimage of y intersection the boundary of M. And so what we're going to get is that the preimage of y is neat, okay? Because we are in this situation in which the intersection is transversal, the intersection between the submanifold and the boundary of the ambient space. So we have a regular value theorem in which what we deduced is that under the conditions in the theorem, conditions that are not very difficult to obtain in applications, that both these maps are actually, both of these maps have y as a regular value, then the preimage of y is a CR neat submanifold of M. At some point we saw when we were just considering differentiable maps between manifolds without boundary that if a differentiable map is transversal to a submanifold, okay, of the target space, then the preimage of this submanifold is also submanifold. And we want to have an analog of such result in which we consider indeed the preimage of an its submanifold. So let's go with that. We are going to introduce this result without a proof. So let A be a CR submanifold of M. And let us consider a CR map F from M to N. Let's assume that either A is contained in the interior of N, okay, or that the image of the interior of M by F is contained in the interior of N, and that A is an its submanifold of N, one of these two properties. Furthermore, assume that both F and the restriction of F to the boundary of M are transverse to A. Then, in such a case, the preimage of A is a CR its submanifold of M, such that the boundary of the preimage of A is indeed the preimage of the boundary of A. All right? What we have to do here in order to prove that, even if we're not going to get into the specifics, is just applying the result that we already know for the case without boundary and studying the points in the boundary of A by considering these two properties, that both F and the restriction of F to the boundary of M are transverse to A. It's a little bit like the result we just proved, in which these two conditions imply, in particular, in that case, that the preimage of Y is not just a submanifold, but a submanifold that is transverse to the boundary. Okay? Here we are going to have a similar situation. The preimage of A is going to be a submanifold, but not just that, it's going to be transverse to the boundary of M, right? So this is the first theorem that we wanted to introduce now. And also we have a version of the Whitney embedding theorem for the case of manifolds with boundary, something that we are not going to prove now either, even if the proof is similar than the proof for the case without boundary. So consider, okay, M be a CR delta manifold, that it is compact and Hausdorff. Then there is a CR embedding of such manifold in R2M plus 1, where small m is actually the dimension of big M. So the result is completely analogous to the result for manifolds without boundary. And of course, the image of big M by the embedding is going to be a manifold, a submanifold with boundary of this Euclidean space. We discussed in this lecture neat submanifolds. Along the lectures, we introduced manifolds without boundary, submanifolds of manifolds without boundary, then manifolds with boundary, then submanifolds of manifolds with boundary, and finally neat submanifolds. In the next lectures, we are going to focus on the properties of the space of differentiable maps. In particular, we are interested in knowing whether some properties in the space of differentiable maps are stable. We studied this concept a few lectures back, and then we used homotopy theory. But the best and most elegant way of saying that a property in the space of differentiable maps is stable is defining a topology and then showing that for such topology, the property defines an open set. Because of this, we are going to introduce a couple of natural topologies in the space of differentiable maps, namely the weak and the strong topologies. And indeed, that's going to be the subject of our next lectures. Thank you for your attention.